Good afternoon, everybody. Welcome to class today. Thank you for joining me, whether you are joining me live or you're watching the recording. I just appreciate you tuning in. Thank you for watching. We're talking more about database normalization today and designing databases for success. Last week, we kind of talked about what normalization is, and I kind of told you all a little story that kind of exhibited the importance of normalization, that kind of took data from an unnormalized state. And then as things changed, as the individual in the story started to have life changes, it forced a database that kept that individual's information to need to have changes as well in order to adequately keep that information. And so at the end of the day, ultimately, that's kind of what we're talking about when we're talking about normalization. We're talking about the process that we design our databases to remove redundant data. And so what we're going to be talking about today are going to be, what can happen if we don't normalize our data, and then the different forms of normalization. First normal form through Bryce-Codd normal form, which is sort of third normal form plus. And then next week, as we kind of wrap up the module and get ready to wrap up the course in general, surprisingly enough, right? Like we are right here close to the end, which is really, really amazing. We'll do a more practical example, kind of taking everything and putting it into place, basically. And so the fact of the matter is, as we are looking at databases, we get data returned from databases sometimes, and there are issues. Right? Some data, for example, is wrong. Crazy thought. I know to have the fact that there might be some data or some information out there to exist that may very well be incorrect. What I'd like for you all to kind of keep in your head just for a brief moment today, just for the time that we will be spending together, that there is a possibility that information could be wrong. And when we say wrong in this sense, it means that there are logically impossible outcomes. Right? And these logically impossible outcomes oftentimes happen as a result of data anomalies. And so when we look at data anomalies, we're really looking at the core of why we normalize. Right, so when we think about why we normalize, we are thinking about, good design techniques. And these are the same sort of good design techniques that we carry forward with us from other classes. Things like, making things easier to read and understand, making things easier to work with. But we also see things like, wasting space. And when we're talking about wasting space, we're talking about wasting space, both space on disk in long-term storage and space in memory in short-term storage. Right? Space on disk is relatively cheap, not a huge deal for us in 2022. Right? So we can kind of work with that a little bit better. But our short-term storage, our RAM, our processing speed, that's where things are more at a premium. And so if we're wasting storage memory there, for those of you who have taken CIS 115, right, the Introduction to Programming and Logic course that we do in Python, one of the things that you've seen me done in that class is you've seen me demonstrate, different sorting algorithms. It's something that we do in the last module in that class. And I will demonstrate, something that takes a short time to run versus something that takes a long time to run. Like a bubble sort versus a quick sort or a merge sort sort of thing. So one of the sorting algorithms, when it faces a big data set, is done really quickly. Within a minute or so. And then the other one, when we look at a bubble sort, it could take several minutes for it to actually handle the big data set. So when we have our data properly normalized and we have all of the data kind of in the tables where it needs to go, then if we have only the important data in the tables that we need to be working with, then that means that only the table data that's going to be parsed and read and dealt with is going to be the data that's going to be pertinent to that query. We won't have extra data that will be adding extra unnecessary steps to our processes, adding process time, and removing speed from our equation here. But then we also have these big problems with our update anomalies. Deletion anomalies, insertion anomalies, and modification anomalies. And these different things can cause problems to our data that can result in huge issues. And I'd like to take some time just to talk about each of these, the issues that they cause, and then as we get into normalization, we'll kind of refer back to these and talk about how normalization can kind of help us fix these. Right? Because when it comes to, really deletion and modification, and when it comes to deletion and modification anomalies, the big thing about normalization there is, that if we are only relying on fully functional dependencies, which we'll talk more about what that means when we get to that point in second normal form and further in third normal form, then we'll be A-okay there. Insertion anomalies can kind of help us out just in first normal form as we're kind of working there. But a deletion anomaly. What is a deletion anomaly? A deletion anomaly exists when certain attributes are lost because of the deletion of other attributes. And so again, one of the things that we'll talk about are functional dependencies and transitive dependencies. Once we start talking about our normal forms. And a functional dependency is dependent on the top, when we think about a functional dependency, it's basically a dependency that is dependent on the topic of the table. Right? So if we have for example, a players table, if we were to, everything that's in the players table should be dependent on what would be the primary key, which would be the player. Right, the player number, which by extension would be the player name, so on and so forth, right? Because it's all it's the player ID. Right, and we'll get deeper into what all that means in just a bit. But when we're talking about a deletion anomaly, one of the things that we've talked about when we talk about our delete queries a couple weeks ago is that when we delete something from a table, when we delete a record from a table, we delete the entire record. And so I've got a little table of classes here. Got a little table of classes here, and this little table of classes is unnormalized as it stands right now. Right, so the idea here is that as we kind of work through this little table of classes, we can work through these different anomalies and we can kind of see how the different anomalies impact a table that is not normalized. And we can see here that this table isn't normalized because it has different values, kind of all put together in the same table, right? We have transitive dependencies in here. We have, fully functional, in here with fully functional dependencies. An argument could be made that this table is in first normal form, because if we really look at this table using the qualifications of first normal form, well, one of the qualifications of first normal form is that using row order to convey information is not permitted, and row order doesn't matter here, so that's a check in the column that it meets first normal form. Mixing data types is not permitted. Well, if we look at the columns here, which is what we're talking about there, mixing data types in a column is not permitted in first normal form. Well, that's not the case here, right? Everything in the column is the same data type. It's it's all numbers and then numerical columns, and it's all strings and everything else. So that's a check mark. Having a table without a primary key is not permitted, and that would be kind of, that could be arguable here, because we have course data and student data kind of mixed together in this one table. But the way we're kind of looking at it, the student number in this case, our student ID number, is kind of serving as the primary key of this table. Course number in this case is a transitive dependency, right? Because the course has a number and the student has a course, but the student does not have a course number. Again, we'll talk more about what all that means when we get there. Right? Address would also be likewise a transitively dependent, right? Because the student has the address, but the course does not have the address. And we can also say that repeating, but that is still a check off in the box for first normal form, and repeating groups are not permitted in first normal form. And everything here is a unique group for each column. So for all intents and purposes, this meets first normal form. But this table also further goes to show us why first normal form isn't quite enough all of the time for ensuring our databases meet good design quality standards, because we're about to apply different anomalies to this database and just watch it fall apart. And the first one that we're going to apply to this is a deletion anomaly. Let's say, for example, that Smith here wanted to drop physics. They don't want to take physics anymore. So in this case, with this database, as the schema has been developed for this database, if Smith here wanted to drop physics, since deleting a bit of information from a database requires deleting the entire record, that would also mean that we have to delete the student's name, we have to delete the student's address, we have to delete the student's student number, because all this information is being contained in the same database. Right? So if they dropped physics and we went in to delete this record, This is the only record they have in this current database, the way that we have it set up here. So if we deleted that record, all of it would be gone. We'd lose all of that information. So if Smith went to, re-register for another class, or, do something else, they wouldn't be able to do it. Because all of their information would be gone out of the database. Their student number would be gone, their name would be gone, their address would be gone, everything would be gone. Because the person who created the database didn't originally take the time to normalize the database. Right, and so that's the kind of thing that we're talking about when we're talking about an insertion anomaly here. And so since everything in this table is not fully dependent on everything else in this table, we end up with issues like that. So even though this technically, by the rules that we are going to set forth, right, we mentioned them, but we're going to make them clearer as we progress. This technically is first normal form. But that's as far as this goes. Definitely isn't second normal form. We're still in a lot of danger of having bad information, of having wrong information, in this event. Right, so that's a deletion anomaly. Let's talk about an insertion anomaly. An insertion anomaly only occurs when certain attributes cannot be inserted into the database without the presence of other attributes. So when we think about, when we think back to the last module, when we think about, when we created our database, one of the things that we set out to do was we set out and we said, okay, when we create this database, we're going to put not null here when we create these. That way it forces us to put information in this column every single time. Right, that way we have to put data in there. But think about that table we just saw again. Right, all the course information was also tied to student information and vice versa. Right, so one of the things that happens a lot, you might have even done it when you started coming to school here, is that you register or you apply, but then you don't register for classes right away. Maybe you wait a little bit to register for classes. Or since hypothetically, like this also includes the classes that are available, if we want to put a new class out there, what if we want to put a new class out there that doesn't have anybody up to take it yet? Right, what if we only wanted to insert some data that existed in this table without inserting all the data that exists in this table, right? What if we want to add a course? What if we want to add a student without them registering for a course? We can't add a new course unless we have at least one student enrolled in that course. We can't add a new student unless we have a corresponding course for them to enroll into. Right? Just based on the way that the schema of this database is laid out. So we've kind of reached this sort of catch-22 with our insertion anomaly here. right? We have to be able to populate every cell for our record here in order to create a new record in our database. But sometimes we're presented with a situation where we can't do that. And that gets back to the idea of dependencies, right? The idea of dependencies. These items that are not fully functionally dependent on the other ones. You know, if I was able to kind of split this database up and have one database for courses, one database for students, and then a third database for registrations, then I can add students, I can add courses, I can add as many of them as I needed to their corresponding databases. And in the grand scheme, and there would be nothing to worry about when it comes to an insertion anomaly, because there would be no unrelated information in that table. Right? That kind of gets us to our idea, that gets us to kind of what we're looking at, what we're wanting here. Right, finally, our final anomaly that I want us to look at is a modification anomaly. Modification anomalies are also called update anomalies. And an update anomaly exists when one or more instances of duplicated data is updated, but not all. Right, so what if, when we look at this table here, we have a couple students here that are, represented more than once. What if something happened where Jones and or Richards, maybe one of them got married, maybe one of them moved. And if you don't select them the proper way, maybe the networking instructor submits a form on behalf of Miss Richards saying, Miss Richards got married, she's Miss Johnson now. To the database administrator. The database administrator looks up students named Richards in networking and changes their last name to Johnson, whereas that same student, still in that algebra class, still has the same last name. Right, so then we have, what we were talking about earlier, right? We have logically impossible data. We have the same student, because they'd still have the same student number, right? They'd both be S30. But they'd have two completely different last names. And so at the end of the day, what you really want is you want to have one singular version of the truth. Right? Not just that you want to have one singular version of the truth, you want to have one singular accurate version of the truth. You want the truth that is represented by your database to be the truth. To be what is true. And so we get there through normalization. And we're going to talk about 4 different types of normalization. First normal form, second normal form, third normal form, and Bryce-Codd normal form. And we can think about Bryce-Codd normal form as basically 3 plus normal form. There is a 4th normal form and a 5th normal form. Those 2 occurrences are so rare in terms of being needed that for our purposes, since we're just kind of learning, introductory stuff here, I don't even want us to worry about those. Right, third normal / Bryce-Codd normal is as far as we would ever, I think, want to go for the vast majority of purposes that we'll ever encounter. We start off with first normal form, and all of these things sort of build on one another, right? So there's a sequence to these normal forms. There's a sequence to these normal forms. First normal form is considered the weakest, and we already have seen how first normal form can be the weakest, right? Like we went through our first normal form checklist to see the 4 attributes that could make a table be in first normal form. And we looked at that table that we had, and that table that we had there with our students and our classes checked off all 4 boxes to have a table in first normal form. But even checking off all 4 of those boxes to get us to what is in first normal form, it was still a pretty bad table, right? It was still vulnerable to our insertion, deletion, and update anomalies. And I think vulnerability and I think weakness, I think these 2 words are good ways to describe unnormalized data and what we achieve out of normalization. Because when I think about normalization here, I think about levels of validity, or the percent possibility that anomalies can occur. So as we increase our level of normalization, we decrease the possibility for anomaly. We decrease the possibility that our data is wrong, and we increase the possibility that our data is valid, that our data is that one accurate version of truth that is real truth. So the further we push our normalization, the better we can kind of sleep at night knowing that our data is less vulnerable to anomaly, which is good. Right? So first normal form is considered the weakest. Second normal form is stronger than first normal form. Third normal form is stronger than second normal form. Bryce-Codd normal form is the strongest type of normalization, in parentheses, that we discuss. Right? There is a 4th normal form and a 5th normal form, like I mentioned. Now, I said these build on one another, right? To get into second normal form, you must first be in first normal form. To get into third normal form, you must first be in second normal form, which means that you also must first be in first normal form. Right, so all of these build on one another. Right, so any relationship that is in Bryce-Codd normal form is also in third normal form, is also in second normal form, is also in first normal form. Right, it cascades on down. You know, it's kind of like that old saying of a square is a rectangle, but a rectangle is not necessarily a square, right? You might have heard that from geometry class. Anything that is in Bryce-Codd normal form, or anything, you know, above, right? Anything that is in Bryce-Codd normal form is also in first normal form. But anything that's in first normal form is not necessarily in anything higher. Right, so let's have a look at first normal form now. Now, on first normal form here, I have 3 items. And I said that there are 4 items in our first normal form checklist. And that's because one of our normal forms, or one of our items in our first normal form checklist, you actually are unable to do ever at all in MySQL. Right, so before we talk about these 3, let's talk about that one, which is the secret 4th bullet point for achieving first normal form. Which is that mixing data types in a singular column is not permitted, meaning that you can't have integers, strings, booleans, all in the same column. But as we know from building columns and building tables, MySQL won't let us do that anyway. Right, we are forbidden from doing that by the software. So by default, we're already checking off one of the 4 boxes for first normal form. So when it comes to first normal form, I only have 3 of them on this slide, even though there's technically 4. Because when you set up your table, when you create your table, you have to create your table with a data type for your column, and it errors out if you try to put data into that column that does not meet that data type. And one of the things that we have here is 1, place all items that appear in the repeating group in a new table. So, what do we mean here by a repeating group? So let's say for just a minute, right, am I on the right screen here? Now I am. Let's say for just a minute, I'm creating a table. And let's say I am creating a table. You know, I kind of want to take it back to what we were doing last week with our preschool students, right? So I have a student ID. I might have a student first name. I might have a student last name. But then I might have parent 1, parent 2. This kind of stuff right here is what we're talking about when we're talking about repeating data. Right? It's the same type of data that's kind of coming over and over and over again. Right? This is the kind of thing that would be better to take and move this to a parent table where I just put parent name, maybe a parent ID, and then I can have a third table that relates these two tables together and shows the relationships between the parents and the students, right? So one of the things that we don't want to see is we don't want to see repeating information. Repeating columns that could take 2 or 3 columns with the same type of data. You know, like if I wanted to make a table of movies, right, I wouldn't necessarily want to go movie 1, movie 2, movie 3 with a director name, right? I'd want the director. I want records of the director with the movie. So one of the things that we can kind of think here when we're thinking about not repeating data is to work vertically instead of horizontally. Right? We're working in the up and down instead of in the side to side. And when we kind of think about the whys of this, like it makes a whole lot more sense. Right? Because like, you know, if when I set up my table, I set it up, you know, kind of like what we were thinking about last week. When I set up my table, if I set it up for 2 parents, and then there's a step parent introduced into the picture, and I have to introduce a new column for the third parent, and then maybe a new column for the fourth parent, and then maybe other students don't have these situations. So for some students, data in this column is populated. For other students, data in this column is empty. Right, we start to see why kind of repeating along the x-axis like that is a less than good thing to do. Right, we'd more rather work on our y-axis, work on our up and downs, just make a new record. You know, even if we are duplicating some things in our new record, it's better than having sort of duplicate information across columns in terms of information type instead of exact information, because of the structure of our schema and how that schema works. Another thing that we want to have is a primary key for each new table. So all of our tables need a primary key, and we've said before that a primary key is a unique identifier that identifies kind of what the table is. So, you know, we might have a student ID number for a student table. And so that table is about, you know, the student information. And another one of the things that we put in there is another thing that really isn't a thing in MySQL, which is using row order to convey information is not permitted. Right? Because when you put things into the table, we can select things, we can move things around. So if it has to be in the strict order that it is when you put it in the table, in order for it to make sense, then you did something wrong. Right, but number 3 here is to duplicate in the new table the primary key of the table from which the repeating group was extracted, or vice versa. And that would become a foreign key in the new table that works as that point of reference, so that we've talked about previously, so that we can relate the old table to the new table, so that we can start to work with those items. And one thing to think about too, as you're kind of sitting down and thinking about, how to move your data around, we kind of talk about it in terms of, okay, first goes to second, second goes to third. But you might end up doing it kind of all in one shot. Right? There's nothing that kind of says that, like as I'm working, I'm not going to just skip from not normalized to third or BC. Right? Because that's the sort of thing that, you kind of end up doing. But ideally, when you kind of have your data kind of set up in first normal form, then you start looking for functional dependencies so you can work on second normal form. Right? So what is a functional dependency? What are we talking about when I say a functional dependency? And all I'm talking about with a functional dependency is a direct relationship. Meaning that one piece of data has a direct relationship to another piece of data. Right? So our first bullet point here says if one set of attributes in the table determines another set of attributes in the table, then the second set of attributes is said to be functionally dependent on the first set of attributes. Right? And the example is that business ID to business phone. Right? Business ID has a direct relationship to the business phone because that business ID, that unique identifier that is the ID of the business, that business has a phone number. That phone number belongs to that business. So there's a direct relationship between that business ID and that business phone number because there's an ownership there. So when we start to get into second normal form, that's what we're identifying. We're identifying these functional dependencies. We're identifying these direct relationships. And so in order to get into second normal form, the table must first be in first normal form. So again, no row order to determine information. No mixing of data types. Gotcha, primary key. No repeating groups of information type columns. And then to get into second normal form, all non-key attributes in the table must be functionally dependent on the entire primary key. And now in a second normal form, in a regular environment, the primary key could be multiple columns, right? Which is why we say entire primary key here. Really, to get us into third normal form, one of the things that we do is we have the ID number, right? Just so we can have a singular point of unique ID to serve as a key. Right, but we have an example here that can help us discuss this, right, which is here. We have this example of this scheme this schema for a database: city, street, house number, house color, city population. So if we look at the key here, we can look at this in multiple ways. Right, because technically if we look at the key, city, street, house number is a key. Right there, since there's no like unique identifier here, there's no house ID, there is city, street, house number, that all of those pieces of data are required to get a unique identifier for a particular house. You need to know what city it's in, you need to know what street it's on, you need to know what house number it is, because otherwise those elements can be duplicated. And so if we have a certain house, which is on a certain street in a certain city, then the house color goes with that. So house color goes with city, street, and house number. City population goes with just city. So we have city and city population, and then we have city, street, house number that goes with house color. So city population doesn't really belong to the key of this particular table with the scheme where in the way that we have it laid out. Right? Because for this particular table, the unique identifier for the house contains the city, the street, and the house number. But in this instance, city population is functionally dependent on the city, which is a proper subset of the original key for this particular table. So what do we do here to get this into second normal form? So city population does not have a functional dependency on the primary key for this schema, city, street, house number, right? Because it's not dependent on house number, not dependent on street. It's only dependent on city. So if we built another table, and we took city population out of this table, we built another table, and in that table we put city, because we need that city column to be the relational point so that we can relate this particular table to that table. We take city and we take city population. Then in table 2, we have our key city, which has the values, which has the other column city population, which is functionally dependent on city. And then in our first table, city, street, house number being our key, because that's the unique identifier for the house. Having fully functional dependency with house color, because the color of the house in that because the house at that at that location in that city is a color. right? So if we just took this and separated that out into a couple tables, then we get from something that is not in second normal form, something that would be in, for all intents and purposes, in first normal form, right? Because we do have, represented by this schema again, we do have, something that checks off all 4 of those boxes that we mentioned earlier. No repeating groups. There is a primary key. Data types are not mixed. And row order does not determine information here. So that works. So it is in first normal form, but it's not in second normal form. But if we take this and we break it into 2 tables, then both of those 2 tables are at least in second normal form. And actually, they're technically, at least one of them is technically in third normal form. So if we look at third normal form, the table should be in second normal form, and no attribute should be transitively dependent on the primary key. Transitive dependency. Things get a little tough with transitive dependency. Right, basically when we have 3 elements that we're dealing with, that's where we get into the idea of transitive dependency. Typically we have 2 elements that are dependent on one another, 2 elements that are dependent on one another, and then kind of the odd one out from each relationship that have this transitive dependence because, the only thing that connects them is really the third element. Right? So a functional dependency is said to be transitive is if it is indirectly formed by 2 functional dependencies. So if we look, for example, at this sort of logic map here that we have in our second bullet, we have an x to the z dependency. X is functionally dependent on y. Y is functionally dependent on z. Now in this case, y does not and is not functionally dependent on x. And we'll see in our next example kind of what that could mean in practice. But we have x and z here. We have x, y, and z here all in the same table. And we can see that there are functional dependencies that connect to these 3 items together. But the only thing here that really connects x and z together is the existence of y, right? Like if we look at this in terms of a chain, x and y are together, y and z are together. But when we look at this relationship between x and z, the link between the 2 is not readily apparent. We call it transitive. And the only thing in this case that is linking them together is y. So what we would do here in turn would be to break them apart. Y and z go over here to do their own thing. Y and x go over here to do their own thing. Which is why one of the easiest ways to get into a third normal or Bryce-Codd normal form database is to have database tables that are limited to 2 columns of data in each table. Right, let's look at an example of that, and hopefully that'll help kind of clear things up. So our book has a functional dependency on the author, right? Each book has a clearly defined author. in our table here, right? In our table here, we have book, author, and author age. And so by default, you might be inclined to look at these three things and say these three things are related, right? Book, author, and author age. And when we start to break it down, when we see, well, the book and the author are related. The book and the author are related. Each book has an author. So if we know the book, then we in turn know the author's name. So the book has a functional dependency on the author. The author, in turn, however, does not necessarily have a functional dependency on the book, because authors have multiple books. So when you are referring to an author, you could be referring to one of dozens of books. Right? If I'm referring to Game of Thrones here, in this case, I am referring specifically to George R.R. Martin. But if I'm referring to George R.R. Martin, in this case, I could be referring to Game of Thrones, or I could be referring to Dying of the Light. Right? That's the sort of functional dependency that we're talking about here. And the author has a functional dependency with their age. Because each of these authors have an age. So, it kind of gets back to that X is Y and X to Y and Y to Z. And so, if we kind of look at a transitive dependency, we could see that how, a book and the author age could be dependent on one another. Right? But it's only dependent on one another because we know the author. Right? It's only linked through that center link, that center chain link of the author name. Otherwise, if we took the author link out of the equation, it wouldn't necessarily make sense. And so that's what makes this a transitive dependency. In order for the book to author age link to hold, you have to have the relationship that includes the book to author. So in order to get us into third normal form, we don't want that transitive relationship to be a part of our table. So ideally what we would do here is we would make this a table. In which case, right, we wouldn't need the second George R.R. Martin. Right, so we can get rid of that one. And that would be a table. And then if we needed to reference the age of the author of Game of Thrones, we can do a simple join, right? Select author age from author info, join book info on author info dot author equals book info dot author, where book equals Game of Thrones, and you get back 66. Right, and that gets us to where we want to go. Now to get us into Bryce Codd normal form, ideally what we would want here, Bryce Cod normal form does not allow dependencies between attributes that belong to candidate keys. Right, so ideally we could probably break this down even further if we were getting to Bryce Cod normal form. Right, third normal form and Bryce Cod normal form are basically the same. You know, it gets a little more specific when it comes to kind of what it's kind of judging. We won't get too deep into it now. It's not a huge deal. If you don't get it all the way to Bryce Cod normal form when you're attempting your normalization for your lab, that's fine. It's not a big deal. Besides, for this lab anyway, one of the things that I want to see is just, I kind of just want to see you try more than anything. I don't necessarily expect you to see you succeed 100%. I just want to see a good effort. So that's a big thing out of this one. So since we've reached our hour, we've actually gone past our hour. That's where we'll stop for today. Next week we'll look at more of a practical example of kind of how we do this in functionality. We'll look at some data and we'll kind of sit down and draw out kind of a table, and we'll actually work to kind of make some of it, all that kind of fun stuff. So that's where we will pick up from for next week. I hope you all have a good holiday this week. We'll hang out in the chat for just a moment, just in case anybody who is here with me live has any questions. With that being said, that's all that I have for you for today. Thank you for watching, and we'll see you next time.